let's take a look at definite integrals and integration by parts. Let's remind ourselves of the integration by parts formula for indefinite integrals. Ready? Write it here. So u times v minus integral of v times du. And we could call that capital F of x, right? It's the indefinite integral. So what would you guess we do when we have a definite integral? It's a little tricky here. We have a u and a v, but really those are shortcuts for expressions involving x or t's sometimes. So here, if we said integral from a to b, we're really saying integral from x equals a to x equals b. Well, one way to do it would be to do whatever this whole expression is, ub minus integral of v du, from x equals a to x equals b. So just take the indefinite antiderivative and then evaluate that at b and at a. So you could say that's big F of b minus big F of a. And that's a perfectly good way to do it. I like that way because it gives me my antiderivative as one unified function. I mean, I'd have to do whatever this integral ends up being, but I get one big antiderivative function, and then I could plot that, for example, rather than having it broken up into separate parts. But another way of thinking about it, and this is what the book is going to push us toward, I mean, not just this book, but pretty much any book, that this definite integral x equals a to x equals b u dv could also be written as uv from x equals a to x equals b. So that's part of the antiderivative, right? And we'll evaluate that at b and at a and subtract the two, minus the integral x equals a to x equals b v du, and then you do that integral whatever way you need to, and then evaluate it from a to b. So one thing to notice here is that unlike in u substitution, we're not translating the x values to u values or v values. We're leaving it all in terms of x, because here the u and the v are just kind of shortcuts for expressions involving x, and we're not really turning the whole integral into integrating using u or using v as its own variable. So we'll highlight we don't turn the x values, the a and the b, into u or v values. And compare that to u substitution, where we do turn them into u or v values. So let's do a quick problem, maybe not that quick. How about the integral 0 to 40 of 4 e to the minus x over 10 times x dx? This e to the minus something times x would be a surge curve, so that would be common in applied probability and a few different areas of engineering. Not a bad idea to plot it. Looks something like this. 0, this goes up to 17-ish, out here to 40. Maybe do a quick lower bound, upper bound, and guess, because this arithmetic is going to get pretty involved. It'd be nice to have some guidelines. So I'd say a lower bound of 0 would be pretty good, right? This integral has to be positive. It's hard to do any better lower bound than that. How about an upper bound? We'd say 17-ish there. 17 times 40 minus 0, which is about 680. And our guess would be about half that. Let's see. There we go. What is that? 340. And it's hard to say whether we think our guess is going to be higher or lower than the actual value. All right, so we've got an idea of the problem. What do we do next? Looks like, can we do u substitution? You should always ask yourself, can I get away with u substitution here? Because that's easier than integration by parts. But if you use u equals negative x over 10, you're still going to have this times x out here. It's not going to work. So maybe integration by parts. What should we use for u and dv? No logs, no inverse trig, algebraic. There's that x there, so we'll use u equals x, and then dv equals whatever's left over, which is what? The e to the negative x over 10 dx. What about this 4? We could just kind of keep that out in front of the integral. So kind of move it out there. So what's the next step here? Figure out du and v. So go ahead and do that before I do it, just to exercise your brain. Du would be dx. dv, what's the integral of e to the negative x over 10? Well, you could write this as e to the ax with a equaling negative 1/10, right? Negative x over 10 is like multiplying x by negative 1/10. So then, so the integral would be e to that same thing times 1 over that, 1 over negative 1/10. So we could write it that way to start with. It's going to be easier. You know, I usually don't like simplifying, but it'll be easier this way if we do simplify that to negative 10, e to the x to the negative 10. All right, and then ready to do the antiderivative, or write the integration by parts formula. So u is x, v is negative 10 e to the negative x over 10. And you probably caught me deliberately making a mistake. I need to have that multiply sign right there. And then minus the integral of v du. V is negative 10 e to the negative x over 10. And du is dx. So I could keep going this way and then apply the 0 to 40 later. But you can probably figure out how to do that. I'm sure you can figure out how to do that all by yourself. Let me show using this new formula from the book. So we're going to say evaluate this from 0 to 40, and this one from 0 to 40. Anything I forgot? That 4 I moved out front. So I need to have 4 times that whole thing. I guess I should kind of put it here, although that's the integration by parts formula. Generically, it doesn't have a 4 out front. All right, so what should we do next? So we'll just copy this part. X times negative 10 e to the negative x over 10 from 0 to 40. And how about this? Do I need integration by parts there? Do I need u substitution? Do I need anything else? That's basically just e to the stuff, or e to the x, so I can integrate it. I could use u substitution, but really I basically just integrated something like that up here, so I can use that same kind of shortcut here. So we'll have a minus here, and then this minus 10 again, and then the integral of that is 1 over minus 1/10 e to the negative x over 10. That whole thing from 0 to 40. So that looks like a lot of fun to evaluate, right? So what can you do from here? Well, really, if I had to solve this problem, I would just go back to the other way of evaluating definite integrals, type my indefinite in, call it big F, and then evaluate it like that twice. But let's just practice the by hand skills here real quick, hopefully real quick. So plug in 40 here. Let's pull out the negative 10 first. Negative 10, 40 times e to the negative 40 over 10. Then plug in the 0, minus 0 times that stuff, e to the negative 0 over 10. And then this part, minus, let's see, what should I do with this? I've got 1 over 10, which is just another 10. Multiply that by this, so we'll have 10 times 10 times, and we'll pull all that out. The two negatives will cancel those, and we get e to the negative 40 over 10 minus e to the negative 0 over 10. Whew. That's a lot of brackets. All right, so at this point, it's a complete math expression. You could type it into Desmos. Can we simplify this a little bit? Well, here I have 0 times something and no infinities involved, so I can just ignore that. Can I ignore this? Well, that's e to the 0. E to the 0 is not 0, it's 1. So I can replace that with a 1. E to the negative 4, I can't do that in my head, I would need a calculator. So you could plug all that in, like I said, or you could also say big F of x equals 4 times, and kind of go back and take off all the indefinite stuff, or all the definite stuff from here, and say x times negative 10 e to the negative x over 10 minus 10 times 1 over 10 e to the negative x over 10, and then do big F of 40 minus big F of 0, and that would be our answer. And then you check that against the upper bound, the lower bound, and the guess. Another way to check would be to just say let little f in Desmos, little f of x equals e to the negative x over 10 x, big F of x equals all that stuff. You could do big F of x, and hopefully that would overlap exactly with little f of x. You could also say integral 0 to 40 little f of x dx, and that will give a number. Desmos behind the scenes will do something like the trapezoid method. So that gives a number that you can then check against this, or if you really wanted to type all that stuff in. So that helps check not only that we did the antiderivative correctly, but that we plugged in everything correctly and didn't make a mistake like e to the 0, accidentally thinking it's 0 instead of 1, etc. One thing I should point out here real quick, you really need this times signal, a times sign right there, and let's see, anything else? That one right there. So just to avoid those multiplies accidentally getting interpreted as just a plain subtraction. All right, I just went and checked, and I did all the arithmetic, or all the algebra right. That was good. Somehow I had misread something, and this wasn't 17-ish. It was 14-ish. So then we'd change our upper bound and lower bound, etc. But anyway, it was pretty close, and doing big F of 40 minus big F of 10 in Desmos gave me the same thing as doing this, so everything's good.